Verify divergence theorem for the vector field f bar equals x square minus yzi plus y square minus zxj plus z square minus xyk taken off the cuboid box where x varies from 0 to a, y varies from 0 to b and z varies from 0 to c. Since we wish to verify divergence theorem, we have to evaluate triple integral divergence of f bar dot dv, as well as we have to evaluate surface integral double integral over s f bar dot n into ds. We have to verify that these two integrals give us the same answer. Cuboid box is a closed surface bounded by closed curve. There are 6 faces for the cuboid box, and each of the rectangular boundaries on 6 faces can be considered as the closed boundaries. Let us first of all evaluate triple integral over b divergence of f bar dot dv. We have divergence of f bar can be evaluated using dou by dou x of the first component function plus dou by dou y of second component function plus dou by dou z applied on the third component function of the given vector field f bar. We obtain divergence of f bar equal to 2 times x plus y plus z. Therefore, volume integral becomes integral 0 to c, integral 0 to b, integral 0 to a, 2 times x plus y plus z into dx dy dz. Notice that here x, y and z have constant limits. Therefore, order of integration doesn't matter. We obtained the volume integral gives the answer abc into a plus b plus c. Now we have to evaluate surface integral over the 6 faces of the cuboid box. Let us denote the bottom portion of the cuboid box A, O, G, B using S1. Let us denote the top portion of the cuboid box D, C, F, E using S2. Let S3 be the portion O, G, F, E. Let S4 be the face A, B, C, D. Let S5 be the face A, O, E, D, and let S6 be the face B, G, F, C. When we evaluate surface integral, we have to notice that n cap is the unit normal vector with respect to the surface considered. When you consider the face S1, which is the bottom portion of the cuboid box, n cap will be equal to minus k. This is because the surface S1, which is the bottom portion of the box, is lying in the xy plane, and we have the outward unit normal will be minus k. If you consider k, it is perpendicular to the surface S1, but it is inward unit normal. In divergence theorem, we have n cap denotes the outward unit normal. Therefore, with respect to surface S1, n cap will be equal to minus k. When you consider the top portion of the box, that is the surface S2, we have n cap will be equal to k cap, because the outward unit normal for S2 will be n cap equals positive k cap. Similarly, we have, when you consider the face S3 of the cuboid box, which is the face OGFE, we have the outward unit normal with respect to S3 will be n cap equals minus I. Notice that the face S3 lies in the YZ plane, and it is the backward portion of the cuboid box. Therefore, minus I will be the unit normal for the face S3. Similarly, when you consider the face S4, which is denoted by ABCD, we have n cap equals I will be the required unit outward normal. We have S4 is the front portion of the cuboid box, and the outward unit normal for S4 will be n cap equals positive I. When you consider the face S5, which is represented using AOED, we have n cap equals minus j will be the required unit outward normal. This is because S5 lies in the XZ plane, and we have j will be the unit normal perpendicular to the ZX plane. But when you consider the surface S5, we have n cap equals minus j will be the required outward unit normal. With respect to surface S5, if you consider n cap equals positive j, it will be the inward unit normal. Since we are looking for outward unit normal, With respect to S5, we have the required n cap will be equal to minus j. When you consider the surface S6, which is represented using BGFC, we have the required outward unit normal will be n cap equals positive j. Notice that along the z-axis, we will get the height of the cuboid box. When you consider the surface S1, which is the bottom portion of the box, we have at S1 z equals 0 because there is no height for the box when you consider the bottom portion. When you consider the surface S2, it has a height z equals c. When you consider the backward portion S3, which is represented using OGFE, we have OGFE lies in the YZ plane and therefore x equals 0 will be the equation valid for this portion S3. When you consider the surface S4 represented using ABCD, which is the front portion of the cuboid box, it has the equation x equals a. Similarly, we have when you consider the surface S5 represented using AOED, we have y equals 0 will be the equation valid for the surface S5 because S5 lies in the ZX plane and therefore y equals 0 will be satisfied. When you consider the surface S6, which is represented using BGFC, y equals b is the equation satisfied by this surface. Now we will evaluate surface integral with respect to each of the surfaces starting from S1, S2, S3 etc. up to S6. We have total surface integral of the cuboid box represented using this expression will be sum of surface integral on each of the surfaces S1, S2 etc. S6. We have with respect to surface S1, z equals 0 and n cap equals negative k is satisfied. Therefore, for the surface S1, in this expression of vector field, you will give z equals 0 here, so that the expression of vector field reduces to f bar equals x square I plus y square j minus xyk, and you will take the dot product between f bar and n cap where n cap equals minus k. When you take dot product between these two, you obtain xy. Therefore, we have surface integral along surface S1 will be integral 0 to b integral 0 to a xy dx dy. Order of integration doesn't matter here, and the range of variation of all the variables have been specifically given in the question itself. Now we will evaluate surface integral along the surface S2. We have S2 satisfies the equation z equals c. Therefore, in the given expression of the vector field f bar, we will give z equals c and we obtain this corresponding vector field. Now we will take dot product between f bar and n cap. Therefore, we obtain f bar dot n cap equals c square minus xy. Thus, surface integral will be equal to integral 0 to b integral 0 to a f bar dot n cap, which is obtained as c square minus xy. Similarly, for the surface S3, which has the equation x equals 0, the vector field changes to f bar equals minus yzi plus y square j plus z square k. Now we will take dot product between f bar and n cap where n cap equals minus I for the surface S3. We obtain the dot product as f bar dot n cap equals yz. Therefore, surface integral along S3 will be integral 0 to c integral 0 to b yz dy dz, which gives us the answer. Along the surface S4, since it has the equation x equals a, we will give x equals a in the given expression of f bar, and f bar changes to this expression. We have for S4 n cap equals I. We will take dot product between f bar and n cap, which gives us a square minus yz as the answer. Therefore, surface integral along S4 will be integral 0 to c integral 0 to b a square minus yz into dy dz, which will give us this answer. Similarly, we have for S5 where y equals 0 is satisfied and n cap equals minus j. When you give y equals 0 in the given vector fields expression, f bar changes to this expression. You will take dot product between f bar and n cap, which gives us zx as the answer. By usual integration, you get the surface integral along S5. Similarly, along S6, which satisfies the equation y equals b, you will give y equals b in the given expression of vector field f bar, and you get the vector field f bar as this expression. You take the dot product between f bar and n cap, which will give b b square minus zx as the answer. Therefore, the integrand becomes b square minus zx. You carry out integration with the limits of the variables already known. In all cases, we have the constant limits, gives us freedom to follow any order of integration. Notice that when you consider surface integral along S1 and S2, ds is equated to dx dy. This is because these two surfaces S1 and S2 lie in the xy plane. Similarly, when you consider surfaces S3 and S4, ds is equated to dy dz because S3 and S4 lie in the yz plane. Similarly, we have when you evaluate surface integrals along S5 and S6, ds is replaced using dz dx because S5 and S6 lie in the zx plane. When you add up all the surface integrals evaluated over S1, S2, etc. S6, you obtain ABC into A plus B plus C, which coincides with the already evaluated triple integral over V, divergence of F bar into dV, and hence Gauss divergence theorem is verified.